Do you know what is common between a sailing ship, a person standing on a moving escalator, and the blades of a rotating fan? Well, all of them have a constant speed, and yet only first two are considered as uniform motion, whereas the motion of the blades of a rotating fan are non-uniform. But what is uniform and non-uniform motion? Let's understand this by using SimPhy, a physics simulator where anyone can create simulations without any coding. First, we'll create a ground, and then place a block on top. Now click on the block, and from the properties on the left side, set the velocity as, let's say, 4 and attach a ghosting tracer with interval as 1 second at the center. Make sure to reduce the simulation speed so that we can observe better. Hit the play button, and notice that the blocks are leaving behind a trace of its images at a regular interval of 1 second. Here these images seem to be equidistant from each other, and obviously this distance is of 4 meters since we gave the velocity of 4 meters per second. And that is why motions where objects cover equal displacement in equal time interval, that is their velocity, not speed, is constant, are called as uniform motion. This means that even if the speed is constant but its direction is changing, then its velocity is changing, and such motions are called as non-uniform motion. For example, look at the velocity of the blades of a moving fan. Here the speed is constant, but its direction is changing. Or look at this ball falling under gravity. Here the direction is same, but the speed is changing. Notice the images are not equidistant from each other. That is, the ball is covering unequal distance in equal interval of time. Or look at this car, where both speed and direction are changing. All these examples are of non-uniform motion. And here things get a little tricky, because we are going to calculate the velocity and position at any time during this motion. But before we get into that, can we calculate the position at any time in case of uniform motion? Let's go back to our previous simulation and draw its VT graph for more clarity. Since the velocity is constant throughout the motion, the velocity graph should be a horizontal line. Here in 1 second, our block covered a distance of 4 meters. In 2 seconds, a distance of 8 meters, that is 4 into 2. In 3 seconds, a distance of 12 meters, that is 4 into 3. So in t seconds, it should cover 4 into t meters, right? Let's verify. I will pause the simulation at any random point, and so the distance covered should be 4 into 1.49 seconds, that is 5.96 meters, which matches with the actual distance. This means that displacement in case of uniform motion is v into t, or area under VT graph. Now, calculating velocity is pointless as it is constant, however. Consider this example, where a block moves with a speed of 2 meters per second for 1 second, and then with 3 meters per second for the next 1 second. Here, what is the velocity of the overall motion? Is it 2? Or 3, or somewhere in the middle? Well, one thing is certain, that this motion is non-uniform as the velocity is changing during the motion. And if we can divide the block's journey into 2 independent uniform motions, then calculating displacement will be easy. And so the displacement will be velocity into time, that is 2 into 1 for this journey and 3 into 1 for this one, covering the total displacement of 5 meters in 2 seconds. So if there's a new block moving with a constant velocity, what velocity should you give such that it covers the same distance as this one in the same time interval? You've 3 seconds to guess. Well, the correct answer is 2.5 meters per second, because if the block covers 5 meters in 2 seconds, then it must have covered 2.5 meters in 1 second, that is, 2.5 meters per second. Where this constant velocity can be considered as an average velocity for the overall motion. In fact, average velocity is actually the net displacement over total time taken. And that's not all. If our block moves with a velocity of 4 meters per second for an additional second, then the total displacement will be 2 plus 3 plus 4. That is 9 meters covered in 3 seconds. So the average velocity will be 3 meters per second. Now let the block travel with 5 meters per second for another second. The total displacement will be 2, 3, 4, 5. That is 14 meters covered in 4 seconds. So the average velocity will be 3.5 meters per second. And if you look closely, there's a pattern here. The average velocity is the average of initial and final velocities. Even if you reduce this interval of 1 sec, and also reduce this uniform change in velocity, the result will be the same. No matter how many times you repeat this experiment, as long as the change in velocity and time interval is same for all the velocities. But here's another thing. Reduce the interval and change in velocity to a value very close to 0, and the graph becomes a perfect straight line. So instead of an increment in velocity of 1 meter per second after every second, the velocity now is changing every moment, that is by dv meters per second every dt time. Such motions are called uniformly accelerated motion, where the acceleration is the rate of change of velocity, or mathematically written as dv by dt. So remember, when the velocity was constant, displacement was the area under vt graph, that is v into t. Here, acceleration is constant, so the change in velocity is the area under a t graph, that is a into t. This is our first equation of motion. And since the average velocity would still be the average of initial and final velocity, displacement is average velocity into t, or area under vt graph. This is our second equation of motion, and the third equation of motion is actually derived from the first two as shown. So to summarize in short, we first discussed uniform motion where the velocity, that is both speed and direction, are constant and calculated its displacement. Then we saw an example of non-uniform motion, which is a combination of two uniform motions and calculated both displacement average velocity. After repeating the experiment multiple times, the VT graph looks something like a staircase. But if we reduce the increment and interval to an infinitesimally small value, then it becomes a straight line. This gave us the three equations known as Newton's equations of motion,